Good afternoon, everyone, or morning. Today my name is Shania and I attend Brigham Young University.
And hi, everyone. My name is Irem, and I attend University of Florida.
Under the mentorship of Dr. Tang, we did this project called Marine Energy Prototype Development from Wave Energy Conversion to Ocean Current Turbine Design. Firstly, want to discuss why marine energy, why this matters. Well, the Department of Energy had looked into this, and approximately 2,300 terawatts of power lie in our coastlines. This is equivalent to 220 million people's homes, so there is a lot of energy. However, efficiently converting that energy still remains a key challenge. On the rightmost side, we have a model of how people have tried to look into this and extract energy from marine resources from a variety of different perspectives. However, engineering new energy conversion systems still remains a difficult task to do efficiently. And that's why our research focuses on wave energy with an oscillating surge wave energy converter and ocean current turbine and OCT.
In order to gather background information for our projects, we started off with looking into existing marine renewable energy technologies and also doing a literature review, including the work of Dr. Tang and his research group have done in the past. For our first project, we looked at a 2024 paper on an oscillating surge wave energy converter with an above the water power takeoff mechanism that converted the mechanical motions of the waves into electrical power. Having the power takeoff above the water allowed for less corrosion for the generator parts and also let us have more efficient energy transmission due to less torque being transmitted into the generator. This paper improved OSWEC power takeoff designs. However, it did have limited experimental prototype validation. For the second part of our project, we looked at a 2026 paper on a buoyancy controlled dual rotor ocean current turbine. This paper introduced the twin turbine design and modeling. However, it did lack in having a prototype for experimental validation. So these scientific gaps helped us to come up with a valid path for the rest of our project, and we decided to look into having a valid prototype and ways to test it for both of these devices. And you can see the devices that we had on the papers, the OSWEC and the OCT. Project 1, Oscillating Surge Wave Energy Converter. An oscillating surge wave energy converter takes in the back and forth motion of waves near the shoreline and converts them into electricity through the use of a power takeoff device that sends this motion into a generator. An OSWEC is designed for nearshore wave energy harvesting. The project objective that we had was to improve and evaluate an existing OSWEC prototype. We were handed down an existing 3D model from previous REU students, so we did not have to start from scratch. We could focus on improving the prototype that we had and simulating it. Here's the 3D design that we were passed down from previous REU students. Before we could improve the prototype, we had to actually produce it. We started off by 3D printing all the parts that we would need to manufacture. We prepared the structural and mechanical parts for assembly. We integrated the power takeoff mechanism and the generator. Electrically, we connected the generator output to an LED. And when we put the mechanism to use, the LED illuminated, telling us that we had a working prototype. Shania is gonna do a little demonstration for y'all. You can see the LED illuminate.
Yeah, it's a little hard to see from far away.
After we had our original prototype, we saw some room for improvements. Mechanically, we replaced the original power takeoff with a chain and sprocket transmission, as you can see in our final prototype that Shania just demonstrated for you, which improved the torque transfer and mechanical reliability. Electrically, we added a Schottky bridge rectifier, which made the components of the circuit to have the right polarity, so the LED could illuminate during both clockwise and counterclockwise rotation.
Next up, concurrently with that, we decided to simulate this device. I will show you a little video. And the bottom we have just the simulation and it's going back and forth like we had just demonstrated, but it's in the computer. So this is a WEXIM, a wave energy converter simulator, and it's software developed by US National Labs. It helps us with faster iterations and also to detect any defects that might be in the model before we have a prototype or a larger scale version. We use this math formula here that goes into the device, and that's basically all the wave and the physics of the waves, as well as putting in the models, the 3D models, friction, torque, and geometry, as well as the PTO. One of the simulation results that we have that I would like to go over is in figure 1 on the right side. This is at a wave period of 2.7 seconds. Approximately a wave is going to come in at 2.7 seconds, and then another one is going to come in and match that time. This tells us how much the flap angle is at and what the converted power output is. And it's important to clarify the converted power is after you take away the electric power from heat from the generator. And this helps us to find the best match for this device in a particular location, which is where we go to this slide, the ideal locations for deployment. WIXIM devices vary. Waves resources devices vary mainly in wave height and wave period by location. For our OSWEC device, it is best in places like Washington or Oregon, where the waves come in at a certain period of 8 to 11 seconds. Since this is a 1 to 10 model, when we scale it up, it matches those parameters. And for a device such as the OCD, which we're going to discuss next, that would be best in locations such as Southeast Florida.
Project 2, the ocean current turbine. The ocean current turbine converts ocean current flow into electricity. It is very much like an underwater wind turbine because it rotates continuously in flowing water. The project objective for this part of our research was to design and evaluate a scale prototype of an OCT. We started off by looking into some literature of existing designs, and we developed a new 3D model based on design concepts and the project requirements that we were given. The biggest challenge that we faced with the ocean current turbine design was selecting a generator. We selected the CubeMars RI-115 frameless motor because of its direct drive operation and high torque capability. Because it was direct drive, the blades that we would design, I'll talk about that in the next slide, would go directly around the generator and we wouldn't need to have any extra gearbox parts. It was also high torque, so it could work in slow flowing waters. So one issue that we had with this generator was that it did not have bearings or a housing. So we had to design a rotor to shaft interface, and we selected the appropriate bearings for it. You can see a cross-sectional view of the proposed generator integration assembly on the bottom left. The next important thing was to design the rotor blades for our rotors. And we chose to have a 3-blade rotor configuration because we thought that it would be the most efficient and balanced option for us. And the blade length was selected from our prototype that we had scaled the blades for. And the geometry was chosen based on previous ocean current turbine designs. And we optimized this for 3D printing as we used the resources that were given to us in the print lab downstairs. So our final assembly, here's a little demonstration for you of one of our turbines. You can see that we were able to get it to light up an LED. It can power much bigger LEDs, but that's just what we had, so it's a little hard to see. We integrated the frameless generator, the bearing supported shaft, and also the 3-blade rotor, and now our assembly is ready for simulation and use in the future for future researches.
In conclusion, with the oscillating surge wave energy converter, we improved upon the existing prototype demonstrated electrical generation and validated it through testing. With the ocean current turbine, we developed a generator integration concept, designed a complete prototype assembly, and established foundation for future fabrication. Both projects advanced the development of practical marine renewable energy systems. Here are the references we used for our project. And we would also like to sincerely thank Dr. Tang for his guidance, mentorship, and continuous support throughout this research. FAU, iSense REU, for providing laboratory resources and facilities and providing us with this valuable research opportunity. Previous researchers whose work served as a foundation for this project. And we'd also like to acknowledge that this work was supported through the NSF REU site in sensing and smart systems. And this work was supported through the NSF Engineering Research Center for Smart Streetscapes. Thank you.
Thank you so much.